the 12.3 notes to start. And again, I placed another pile on your desk because, you know, I have a lot of students that keep accidentally getting, not accidentally, but ended up quarantined that weren't really expecting to be home. And I just want you to have materials available to you just in case. So we are going to start right at the top of 12.3. These are called infinite series and sequences. As long as you can write a formula for these, you're going to be able to take limits as well. So we're going to do a review of limits, and we're going to do the sum formula for an infinite sequence and series instead of the finite ones that you did before. All right, so up at the top, I think you have a little bit of space here. An infinite sequence is just a set of infinitely many terms. So this is just infinitely many terms. And hold on one second, let me make sure I'm sharing the right screen. There we go, that should fix that. So we're going to take a sequence and we're going to be writing a formula for it, kind of like you did last week. So you'll see some arithmetic, some geometric, and you're also going to see some that are more patterned based, like perfect squares. The factorial, I realize you guys really haven't ever seen that in the past, so we'll talk about that a little bit more in depth today too. And then you'll be taking those and you'll eventually be putting them into what's called sigma notation with the big E again. So we do a little bit more with that today. So when you did limits in the past, we say as n approaches infinity, if you have 1 over n, what you were taught to do is think of n as a really large number, like 100 million. And what we say is when you take 1 and you divide by something really, really large, it produces a value so small that we say it approaches 0, and therefore your limit is equal to 0. Okay, so it's kind of a refresher from, we did these with your partial fractions, so it would have been around Christmas time, so a couple months back. So number 1, I gave you a limit of n plus 1 over 4n, and you want to find it as n approaches infinity. So what you want to do to evaluate these limits is you want to divide each term by the highest power of n that you see. You're going to divide each term by the highest power of n that you see. And again, these always kind of follow patterns too. So eventually, once they come back to you, you don't have to show every little thing. So by highest power you see. So here's your review one. So I have degree 1, so just n. So I'm going to go the limit as n approaches infinity, and I want to go n divided by n, and then I'm going to go 1 divided by n, and then I'm going to go 4n divided by n. And then you're just going to go through this and see what these approach. So top fraction, n divided by n, that just cancels. So that's just equivalent to just plain 1. And your next expression, the 1 divided by n, again, what you want to think in your head, just like before, is 1 divided by a huge number. So what is this approach? 0. Yep, so that approach is 0. And then on the bottom, I would just cancel the n's, and I would just be left with the 4. So my limit is just equal to 1 plus 0 divided by 4, which is just plain 1/4. So it's just equal to a 4th. You guys remember doing those? Okay, I know it's been a couple months though. You'll see 2 that are a little bit different, but everything else is pretty much a review. So number 2, I want to evaluate this limit. So what's the highest power up here? Yep, n squared, good. So I'm going to divide every term here by the n squared. So divide by n squared, divide by n squared. I'm going to do 1 divided by the n squared. And then I'm going to do the 2n divided by the n squared. And see what these approach again. So I tried to give you one of each different scenario. So your top fraction, n squared over n squared cancels. That's just 1. Your next fraction, 1 divided by n squared. Again, just think of n as a really large number. So what would this approach? 0, good. And then I have here, so I'm going to go 2n divided by n squared, and that is going to approach 0. So I keep going. If you want to write this step, you can, you don't have to. So this would be 1 plus 0 over 0. And can you divide by 0? Nope. So what do we say? The limit does not exist. Yep, you're very close. So this one is just it does not exist. So over to 3, I'm going to divide by the highest power of n that I see, which is n cubed this time. So I'm going to go negative n to the third, and then you're going to divide this by n to the third, and then plus n divided by n to the third, and then I'm going to divide that by n to the third over n to the third, and see what these approach or reduce down to. All right, so my first value just reduces. So this is just going to give me a -1. And then my next value, so n divided by n cubed, that is going to approach 0. I mean, you could reduce it down too, but it still gives you 0 regardless. And then my one on the bottom, that's just 1. So this limit is equal to, I have -1 plus 0 over 1. So this would be equal to, yep, -1. Sorry, I don't mean to write a plus sign there. I was just fixing it. So equals 1. Good. Now your next two, you really haven't seen these yet. So these are your two limits that work a little bit different than the top ones. So your next one, you have 1 divided by 2 raised to the n. So again, this is different. What you're going to do in this case is you are going to plug in a large value for n. So it's different. I'm going to use 100. Again, it doesn't matter. It's just to kind of help you put some numbers in here to get a basis for what's happening. So this is basically 1 divided by 2 raised to the 100. Don't even try putting it in your calculator. It's not going to work. But the point is, if I do 1 over that huge number, what is that approaching as well? 0. Yep. So same idea. So again, this would just be approaching 0. Okay, so if you see that case in the future, you're just gonna, again, think about plugging in a really large value for n. 100, 1,000, 1,000,000, whatever you want to do, but just don't bother trying to type it in the calculator. The next case, I don't think this printed in your notes or not, but I would like you to include it if it didn't. What makes this problem different is right here. I have a -1 raised to the n. And I have to consider the fact that n could be even or odd. So I want you to write this note down, or I'll kind of copy it over here too. So what you want to think about is that -1 raised to the n, if n is even, what would happen in this case is if you raise a negative to an even power, it's going to make it positive. So this is equal to a positive value. We're on the 12.3 notes. Nope, you're fine. Take your time. And then if you have -1 raised to the n, but this time, if n is odd, then what that's going to give you is a negative value back. So for this case right here, what's going to happen is your sign is going to alternate. So this limit works a little bit different. So your sign alternates. So I'll show you this, but then again, if you see it in the future, you can kind of just immediately know the answer. So we think of it like this. So -1 raised to the second or -1 raised to the third is going to give me a positive or a -1 because of those signs. And now I do my limits. So now I'm going to take all my n's and divide them by n squared. So times, and I'm going to go n squared over n squared. And then I'm going to go the other one. So I have 2n squared over n squared minus 4 over n squared. The plus and minus 1 you can keep writing. And then what do we get from this? Okay, so n squared over n squared is just 1. 2n squared over n squared is just 2. And then 4 over n squared approaches 0. So this is really going to just give me 1/2. Well, this limit does not exist because what's going to happen is you're going to alternate signs between your terms. So when you see that -1 to the n, if you want, you could just immediately say doesn't exist because of those alternating signs. Okay, that case is new to you though. So it doesn't exist because your signs alternate. Okay. So what we did last week is we did the sum formula for a finite geometric series. And your sum formula for the finite series, I'll put it up here just in case you want to reference it. We did S of n equals, we did a sub 1 minus a sub 1 times r to the n divided by 1 minus r. You guys remember that? So that's the formula for the finite geometric series. And then we're going to talk about, well, what if it goes on forever? So here is the formula for an infinite series. And the deal is you can't do it if your R value is greater than 1. So your value for your common ratio, this means if and only if, it has to be less than 1. If it's greater than 1, you just say your limit as s approaches infinity just does not exist. So here's the sequence. So you want to find the sum as you approach infinity for 2/5, 6/25, and 18 over 125. The first thing you have to find is your ratio. So you're going to use your calculator and you're going to find your R. Again, if you're not great with patterns, it's okay. So I'm going to give you a formula just for those of you that will second guess yourselves. Your R value is always your second term divided by your first term, or your third term divided by your second. So I'm going to type this in. So you would do 6 over 25 divided by, and you're going to do 2 over 5 in your calculator, and then hit math, enter, and whatever you get here is your R. Again, this one might be easy to just look at and see, but I understand that sometimes you get to ones that you're like, I don't know what it is. Did we get 3/5? Perfect. So this is equal to 3/5, which is equal to R. Okay, so now you're going to ask yourself, is this possible? Is my R value less than 1? 3/5. Yes. So I'm going to say 3/5 is less than 1. Therefore, yes, you can do your sum. Otherwise, you would just stop and say it doesn't exist. So now I'm going to use the sum formula. You'll see it's really similar to this one. So the sum formula for the infinite series is equal to a sub 1 divided by 1 minus r. So this is equal to a sub 1 is 2/5. And then you're going to go divided by 1 minus 3/5, math, enter if necessary. I think this works out nice, actually. I think it's a nice whole integer, if I'm not mistaken. Oh, I didn't write it down. You guys get an answer? Is it 1? I don't know. Let me check. You got 1. Yes, it is 1. Yeah, you could actually do that in your head, couldn't you? Now that I actually look at it. Yep, so equal to just 1. How's that formula so far, okay? Good, and again, it's not one that you have to memorize either. It'll be on, you know, your final exam for you too. So here's another. So your sequence goes 3/4, 15/8. So first thing you want to do is find the ratio. Second term divided by first term, if you're not great with patterns, this works every time. So I would go 15/8, and you would take that and divide it by, what does that say, 3/4? It's getting kind of blurry on me. 3/4. All right, what do we get, 5/2? So now you're going to check it. In order to do the sum of an infinite geometric series, the ratio has to be less than 1. Is that less than 1? No. So I'm going to say 5/2 this time is greater than 1. Therefore, the sum as you approach infinity does not exist. Done. So really easy, actually. But again, just give some reasoning as to why. So 8. I'm going to look at this one and again look for my common ratio first. So I'm going to say my common ratio is equal to, again, second term divided by first term if you're not great with the pattern. So this would be 1/150 and divided by 1/15. So my R value is just 1/10. All right, this time is it possible? Yes. Yep, so I'm going to say here that 1/10 is less than 1. So good to go. Now you're going to just place that into your formula. So your formula, I'm going to do the sum as I approach infinity equal to a sub 1 divided by 1 minus r. All right, so the sum as you approach infinity, a sub 1 is 1/15 and 1 minus r. So this would be 1 minus 1/10. And again, if anything gives you a decimal, please just change it back. I don't know if this does or doesn't though. So 1/15 and then divided by 1 minus 1/10. I got 2/27. We agree? Perfect. This is just equivalent to just 2/27. Again, nice, easy formula. It either exists and you find it, or else you just say it doesn't exist because of the ratio. All right, so these next two problems are actually just review. So you want to find an expression for the nth term of your sequence. So when you're looking at a sequence, first thing I would suggest is look and see if there's a pattern and if it is arithmetic first. So your arithmetic uses what operations? Yeah, very good. Addition and subtraction. So try that first. So is this an arithmetic sequence? Yes, because you are adding 5. Perfect. So now you're going to write the formula. Again, these are the same formulas that you did for homework. So you are going to write what is called the explicit formula for an arithmetic sequence. So explicit formula. So your quiz tomorrow, those will be right at the top of your quiz. You don't need to memorize them. So we're going to go a sub n equal to a sub 1 plus d, and then times n minus 1. So you have a sub n, just general formula. A sub 1 is 6, common difference is 5, and then n minus 1. Make sure that you don't ever add the 6 and the 5. Order of operations means you have to do this multiplication first. So I'm going to have a sub n equal to 6 plus 5n minus 5. So therefore your formula and answer is just 5n plus 1. You don't need to find a specific term. You were just looking for formula. Oh, that's still okay? Bless you. Still good? Awesome. So number 2, is that one arithmetic? No. What's this one instead? Yep, this one's geometric. That means it has a constant multiplier, which is called a constant ratio. So your ratio this time is equal to just -3. I think you can see that one without having to do the second divided by the first. But again, that works every time too. So this one's going to use multiplication. And you are just going to do out your formula. So multiplication. So I have a sub n equal to a sub 1 times r to the n minus 1. So we have a sub n equal to -2 times -3 raised to the n minus 1. And it's okay if you just leave it like that. So you don't have to go any further. You don't have to distribute that exponent. How's that one? Still okay? All right. So now we get into some patterns that aren't arithmetic or geometric. All right. And what you're going to have to do is express these using formulas. So here's some common patterns, and you're going to want to refer back to this page for homework for sure, because it's definitely very helpful until you kind of start to memorize some of these patterns. So if you have to produce even numbers and you need to write a formula, it's just 2 times n. I'm sure that makes sense. Next, if you have odds beginning at 1, then you're going to write that as 2n minus 1. If you have odds starting at 3, you're going to write that as 2n plus 1. And again, it's always assumed that n equals 1 is your first. So this would always be like your a sub 1, a sub 2, a sub 3, unless stated otherwise. The alternating signs, we just discussed that one. So that was the one we did with the limit. And when your signs alternate, it's the -1 raised to the n, because the n can be, again, an even or an odd power. Your squares. So this comes from, so this would be 1 squared, and then 2 squared, and then 3 squared. Then you have your cubes. So to express cubes, underneath this, just in case you want these. So this is 1 cubed, 2 cubed, 3 cubed, so on and so forth. And it's just kind of getting comfortable with recognizing those patterns. All right, this next one, again, it kind of occurred to me later in the day that you guys have not seen this at all, a factorial. Okay, I'm sorry, that's weird. Sometimes things get cut from earlier grades and it's like nobody tells us. So the symbol right here, I'll show you how to get it on your calculator in a second. So here's what your factorial or factorial stands for. So if I have, for instance, this 1 right here, I get it by doing 1 factorial, and that is just equal to 1. Now if I want to get this 2, so this is the second term of my sequence. So this would correspond to 2 factorial. And what you do is 2 times 1. This next term, the 6, would come from 3 factorial. And 3 factorial is 3 times 2 times 1. So the next number, this 24, should be 4 factorial. And that would be equal to 4 times 3 times 2 times 1. Do you see why we abbreviate it? Yeah, because as I keep going, these get bigger. So the 120 is 5 factorial, which is 5 times 4 times 3 times 2 times 1. And you just write it with a little exclamation point right after it. So here's how you find this on your calculator. All right, so on your calculator, someone pick a number. 7. So 7, and then you're going to hit math, and you're going to go over to probability because that is what this is based on. And then do you see choice 4 in there? That's what you're going to pick. And that is called a factorial. All right, and it just gives you the product of all those values multiplied out. So it is math, and it is a function of probability. So you go over to probability and you pick choice 4. I'll write that in your notes for you. All right, so to get your factorial on the calculator, you're going to hit math, over to probability, and it was choice number 4. Okay. So that pattern is a little bit tougher to find. So again, that's why I mean you might want to refer back to these notes if you need to, because that I know is new to you. You're not going to recognize that set of numbers as factorials. Next, so powers of 2. So this 2 represents 2 to the first. This would be 2 to the second, 2 to the third, 2 to the fourth. This would be 3 to the first, 3 to the second, 3 to the third, so on and so forth. So that would be 3 to the end. The other guy would be 2 to the end. Good so far? Mm-hmm.
So should we know?
No. No. You worry, Jake. Yes, Jake, memorize all these by tomorrow. I'm kidding. All right, so what we're going to do with those patterns is we're going to use them to write an expression for your sequence. All right, so we're going to look at some patterns here and see what you think. So here's some advice on these. And again, these are not going to follow arithmetic or geometric. These are going to be the pattern ones. So I'm going to first go over one. And I'm going to think about what is happening here. Would you guys agree the top stays the same? Okay, so formula for the top is just plain 1 divided by. And now I'm going to look at the bottom. And these are just things to help you. So this one is my first term. This would be my second term. And then this would be my third term. And this would be my fourth term. And I'm thinking about how are we getting these? So the bottom, what kind of pattern is that? 1, 4, 9, 16. Flip your sheet back. 1, 4, 9, 16. Perfect squares. And what is the expression for perfect squares? Oh, you guys should know that. N squared, exactly. That's all. So those are perfect squares. That's it. There's your first pattern. All right, now I'm going to look at my next pattern here. So I'm going to start with 2. And then again, I'm going to go here over 1 just to kind of help myself. And then I'm going to think, all right, this is my first term. And again, the 3 is my second on the bottom. And the 5 is my third. And then 7, because you can start however you want here. So I have a sub n equals, what kind of numbers are on the bottom? Odds, and what do they start at? 1. So therefore, this is going to be 2n, perfect, 2n minus 1. Now you're going to look at the top and figure out what's happening. So I started with term 1 and it became a 2. Term 2 became a 4. Term 3 became a 6. What are we doing? Doubling. So evens, right? How do I express evens? 2n, perfect. So now look at your next. And again, you're just looking for, can you see these patterns? All right, so this one I'm going to put over 1 immediately because I think it's helpful. And again, this is a sub 1. And then scan this. So you see 4, 16, and then 64, right? So to me, what jumps out is this is probably powers of 4. So now think about how you would get these. How do I get 1 with a power of 4? 1 equals 4 to the 0. How do I get this 4? 4 to the first, and then 4 to the second would give me 16. So my formula, if I start writing this, the top is a consistent 1, and the bottom is 4 raised to the something, but it's not raised to the n. You're so close. You just say n minus 1. Awesome. Yep. So 4 raised to the n minus 1 because you're just 1 back. So again, this was term 2 and term 1 gave you the 4 to the first. So same thing over here. So I'm going to write this. I have 1, 3, 9, 27. So what powers do those look like? Powers of 3. So this 1 is 3 to the 0. This 3 is 3 to the first. The 9 is 3 to the second. The 27, 3 to the third. Again, we don't start with the 0. So this is my first term. So I have to subtract 1 off my exponent again. So my rule is going to be a sub n equals 3 raised to the n minus 1. And again, when you write those formulas, they definitely should work. Okay, how are those? Okay, so moving into some more with your sigma notation, which I told you we're going to do again. So sigma notation, how to evaluate it, how to expand it, and how to write it. So number 1, I want to go through the calculator again. This one's very easy to do in the calculator. Every calculator in here should be able to do it. So what you're going to do to type that in again is you're going to pull up your catalog. So you're going to go to second number 0. And then you're going to hit alpha, alpha. And I realized it's faster if you hit T. And then instead, if you go up 1, there's your summation. I think that's a little faster. Hit enter. And now you're going to type this in. So this was x equals, thank you. So x equals 2, all the way up to 20. And now in your summation, don't type anything else as far as parentheses go, just place it in there. 2x minus 3. And hit enter. Did everyone get 361? Jake, you too? Yeah. Perfect. Yeah, the basic ones, every calculator in here should be the same regardless of operating system. So that one is 361. That's right from your catalog again. The next one I'm going to actually have you expand out instead. So this one you're going to go calculator. What we did is you hit second number 0 and you go and you find summation. And for the really easy ones that don't involve a ton of parentheses, that's what I would kind of steer you towards. So this one, bless you, is 361. Okay, this next one, because it only goes to 7, I'm going to change your directions, and instead of evaluate it, I want to see your expansion, because you'll see that phrase on homework too. So we're going to expand this one. That means you got to show the work. So I'm going to start at 1 and go all the way up to 7. Bless you. Now this -1 raised to a power should be kind of familiar. This is the one we did with the limit, and this most likely will alternate signs. So see if you can find a pattern. So I would go -1 raised to the 1 plus 1 times 2. That is my first term. Plus, now I sub in a 2. So I go -1 raised to the 2 plus 1 times 2. Okay, I'm going to just have you look at those first 2 terms and see what happens. Because a lot of these work this way. If I take a negative and raise it to an even power, what does it become? So this becomes 1 times 2, which means my first term is just plain 2. Now I go to the next one, so plus. What happens when I raise the negative to an odd power? Negative, yep, just like we saw in the front, times 2. So this becomes a -2. What do the first 2 terms do? Cancel. And I will have to do this 7 times. So now aren't they gonna follow the same pattern? Yes. So here's term 1, 2, 3, 4, 5, 6, 7. All right, what's left? Cancel, 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 2. Okay, so just like that. So that's where that pattern came from, again, on the front. Number 3, you're going to notice something at the top there. I know it's really small. This is your sigma notation as n approaches infinity. So you can't type this in the calculator. What you have to do instead is use the sum formula. So because of this, we're going to do the sum as we approach infinity is equal to a sub 1 divided by 1 minus r. Because everything is actually right there for you. The 5 is the a sub 1, the r is the 3/4. And that's what you'll do on the back is we're going to just reverse it and you're going to write these. So this would be 5 divided by 1 minus 3/4. I think this is 20. Yes, this one comes back as 20. So calculator, and then you're good to go. Equal to 20. All right, how do you guys feel on those so far? Good? All right, just a little bit on the back. Teeny bit, because the other ones we're going to save for a quiz review for tomorrow. And add on a couple. All right, so now what you're going to do is you're going to have these sequences or patterns, and you're going to write the sigma notation. It's not hard. So first sequence, does anyone see a pattern? I hope. +2, right? So this is back to an arithmetic sequence. So this is arithmetic. Common difference of 2, where a sub 1 is equal to 3. So you really don't do anything different to start this. You take the formula and you write it and substitute into it, and then just write your sigma notation with it. So I go a sub n equal to, I go 3 plus 2, and then n minus 1, and then distribute. So a sub n would be equal to 2n. I'm going to just consolidate this at the same time. And then 3 plus the negative 2 would be +1. So then you draw your sigma notation. That becomes your formula. We almost always started at 1, but obviously plug it in and check. If I plug in n equals 1, do I get 3 back? Yeah, so you're good. And now what you have to do is think about, how do we get 37? Let's see, 2 times 19 is 38, so go 1 down, 18, right? 36 plus 1, and then there you go. All right, so number 5, same deal, but this one instead has a pattern to it. So this is a patterns-based one. Again, I just want to expose you to those often so you can kind of pick up on them. So this is over 1. So I have a sub n equals 1 divided by, and what is listed on the bottom again? 1, 4, 9, 16. Yep, perfect squares. So perfect squares are n squared. Now you're going to write your sigma notation. So sigma notation, 1 divided by n squared. It starts at 1, but where does it stop? Infinity. Excellent. So actually, it's kind of easier to do. So just like that. Next. So 7, 11, 15, 19. So this sequence is not pattern-based instead. This one is your arithmetic. I mean, it does technically have a pattern. I shouldn't say that, but you can write it with your formula. Common difference of 4, in which a sub 1 is equal to 7. So you're going to go a sub n equal to a sub 1 plus d times n minus 1. So I have a sub n equal to 7 plus 4n minus 1. Distribute, combine like terms. 4n plus 3. Sigma notation. So 4n plus 3. Beginning at 1. You got to get 63. All right, so 4 times 15 is 60 plus 3, that works. I say 15. 15 is where that would stop. All right, and then this one. This one, again, I hope when you look at it, it should jump out as a pattern on the bottom, and the top is just increasing by 1 here. So what's the pattern on the bottom? What kind of numbers are these? Odds, but they begin at 3. So this is odds, and then you're going to use 2n plus 1 for the bottom. And this on the top is just n. You start with from 1, 2, 3, so on, all the way up to 7. So this one I'll write pattern next to it so that you know it came from that list. So I go a sub n equal to, and my pattern is n divided by 2n plus 1. And then you're going to place it into your notation. So n divided by 2n plus 1. So this is n equals 1. This one's easy, goes all the way up to 7. Okay. How do you guys feel on those still? Pretty good? Not terribly difficult? Okay. Your one on the bottom is just your formula that we used again last week for the sum of the arithmetic series, because I know we didn't do that one today. And then if you draw, we'll pick up there tomorrow because the back 3 problems are quiz review anyways, and then I'll kind of add on a couple more. Comfortable on those? Okay. I was gonna say, you've got like 5 minutes before announcements. Homework, you had those, right?